Hi, I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. Today we're going to talk about how to solve for binomial distribution problems. As our first example of solving for binomial distribution problems, let's consider parts received from a supplier in a manufacturing environment. Suppose that all parts supplied by this particular producer or supplier contain 10% defects. Suppose further that we randomly sample 5 of these parts, that is, n equal 5. What's the probability that exactly 2 of these parts are defective? In other words, the probability that x equals 2, given 10% defects in the general population and a sample of size 5, is what? So in solving for a binomial problem, we have the value of n, but we need the value of p. Since 10% of the population are defective, p equals 0.10. So let's summarize the problem as we have it now. The sample size, or n equals 5. The proportion of the population that possess this characteristic, being defects, is 0.10. And we are going to solve for the probability that x equal 2. Okay, in solving for this particular problem, remember that we are going to sample 5 parts. One way to think of it is we reach out and we grab 5 parts in a pool and we study them and examine them. Another way to look at it, though, that kind of helps me, is if you view it as sampling 5 parts, but sort of one at a time. It gives you a sense or notion of order. So let's look at it that way. We're going to sample 5 parts. We want to find exactly 2 defects. So let's write this down. A defect on the first one, a defect on the second one, a good one on the third one, a good one on the fourth one, and a good one on the fifth one. A sample of 5 parts, 2 defects. Notice that I use the word and. Usually and denotes the multiplicative law, or we're going to multiply. In this particular case, it turns out it's the special law of multiplication because we have independent items, because each part is independent of the other ones. So in any particular one instance, the probability we have a defect is 0.10, and another defect is 0.10, and a good one, which is q, the value of q is 1 minus p, or 0.90, probability of a good part. And so on and so on. Now, because we want all of these things, we are going to multiply them together. And when we work that out, we get 0.00729. This is a very small probability. However, it turns out in the binomial distribution, because sample size is 2 or more, we have to be concerned or worry about the sequence of items, because there are many ways you can get these things. For example, in this particular one, the first 2 items that we sampled were defective and the last 3 were good. But we understand that the last 2 could have been the defects, the first and the last, the middle 2. There are a whole lot of other ways to get this. So let's look at another one. For example, we could have that the first item or part is the defective, the second one is good, and the third one is a defect, and the fourth one is good, and the fifth one is good. Well, let's work that one out. Probably at this particular point, you may be getting restless listening to me talk about this because you may have already seen that we're going to get the same numbers here because we still only have 2 defects. Because of the commutative property of multiplication, x times y equals y times x, it really doesn't matter what order we have the 2 defects. We're going to get the same particular answer when we multiply them out. So we begin to see that we don't have to recompute these over and over and over to get the answer. There is a way to summarize what we have so far. We can say that no matter what order we have them in, we're going to have 2 defects and we're going to have 3 good parts. So when you multiply 0.10 times 0.10, you have 0.10 to the second power. And 0.90 multiplied 3 times is 0.90 to the third, which works out to be 0.00729. So at this point, we have the particular number for an individual sequence or order. What we need to figure out next is how many orders or sequences are possible in this particular problem. That is, how many possible ways are there to get 2 defects out of 5 items? Okay, so how many different sequences or ways can you have 2 defects out of 5 items? Let's go back and write out what we had before. When we first put this problem down, our first 2 were defects and the last 3 were good ones. And then we came up with another way that went like this. In each case, we got the same individual probability as summarized by 0.10 squared and 0.90 to the third. Well, there are other ways to get 2 defects out of 5. And here are some of them. So here's a complete listing or roster of the possible sequences of ways you can get 2 defects out of 5 parts. In any one particular sequence, the probability of getting that sequence is 0.00729, as we have computed it previously. And as you can see from our shortcut notation up here, this would work out to be 0.00729. If we count all these sequences, it turns out that there are exactly 10 ways that you can get 2 defects out of 5 parts. So we can get 2 defects this way, or this way, or this way, or this way. We learned from our probability rules and laws that when we use the word or, it usually has to do with the addition law or additive property. So in this particular case, we will need to calculate each individual probability and then add them up to get a total. Or since each individual probability is the same, we can merely come up here and weight this by multiplying by 10. So that way we get the total probability that we would get exactly 2 defects out of 5 parts. If you work this particular probability out, you get an answer of 0.0729, or 7.29%. That is, if 10% of the general population are defective, and I randomly sample 5 parts, the probability that you will get exactly 2 defects is 0.0729, or about 7.29% of the time. So the value of 10 was determined by writing out all the possible ways that we can get 2 defects out of 5 parts. Suppose, on the other hand, though, we're sampling 25 parts and we want 7 defects. If we started writing out all the possibilities, we would be here all day, and it would be a very, very overwhelming problem to work. We've discovered that there's a shortcut way to determine this particular value of weight of how many different sequences. And this value can be determined by using combinations. In this case, the combination of 5 things taken 2 at a time. That is, we sampled 5, and we want to get 2 defects. If you work out this combination, it will tell you how many different ways you can have this particular problem occur. So let's talk about solving for combinations. In this particular problem, this combination is solved for by writing n in the numerator as a factorial, that is n factorial. And then we write the x factorial in the denominator times n minus x. In this case, 5 minus 2 is 3 factorial, and generally speaking would be n minus x factorial. We can solve for this particular combination because a factorial is 5 times 3 times 2 times 1, 2 factorial, and 3 factorial. And this part of the combination cancels. 5 times 4 is 20, divided by 2 equals 10. And that's how we solve for this value. We can now write out what is sometimes called the binomial probability formula. The binomial probability formula has a combination times p to the x times q to the n minus x. And that's what we just used to solve the defect problem. This particular part of the binomial probability formula yields or gives us the probability of getting one particular sequence. This part of the binomial distribution problem tells us how many sequences. So generally speaking, in solving for binomial probability problems, what we're really doing is figuring out the probability of one sequence and weighing it by how many sequences to get the total probability of this problem occurring. Let's go back to the defect in manufactured part problem and think about the answer that we obtained. In sampling 5 parts with 10% defects, the probability that x equal exactly 2 defects was 0.0729. Is this a high probability or a low probability? Well, obviously it's a low probability. Well, why is that? Well, if 10% of the population are defective, how many defective parts would you expect to get out of 5 parts that we randomly select? Well, the binomial distribution has something called an expected value or a long-run average, which is represented by mu, just as it was in earlier chapters. And mu equals n times p in a binomial distribution. So in this particular problem, mu would equal 5 times 0.10 or 0.50. That means that if we were to continuously, over and over and over, sample 5 parts, we would expect to get about a half of a defect. Of course, this is what we call a discrete distribution, so you can never get a half of a defect. So what would be the more likely number of defects you would get? Probably 0 defects or 1 defect. So how often would you get 2 defects out of 5 when you really should only get 0.5? Well, about 7.29% of the time. As a matter of fact, 2 out of 5 is actually 40%. So in this particular problem, 10% of the population are defective, and we're asking for 40% of our sample to be defective, and that goes against the odds.